Okay, all right. Sorry, I was just wrangling up a few people, as is the case with the University of Auckland spread halfway around the city. We're all over the show, so Mick's coming down to my office to watch, but Sjoerd is in Newmarket. Welcome everyone to this month's QuakeCoRE seminar series, and we're really lucky here to have today Sjoerd van Ballegooy from Tonkin and Taylor. So he's just walked across the train tracks from Tonkin and Taylor to the Newmarket campus, and he's going to present sort of the culmination or the grouping together of a range of different projects looking at different historical earthquakes and the liquefaction observations and assessment procedures. So over to you, Sjoerd.
Thank you, Liam. Right, I will be bringing a little bit of a industry perspective today, not necessarily looking at the detailed modelling of liquefaction that might be done through fancy numerical simulations, but more looking at some of the simplified procedures that industry use to predict liquefaction. It is a big issue. Over half of the losses that occur from earthquakes in recent times in New Zealand can be directly attributed to the secondary loss caused by liquefaction. So you get earthquake shaking, and then if you get the wrong types of soils, liquefaction follows after earthquake shaking, causing considerable additional damage. And most of our cities and infrastructure crosses floodplains, is built on alluvial plains, and so liquefaction is a really big problem. And when things get designed and built, liquefaction constantly needs to be evaluated. And as an industry, we sort of use simplified procedures because we just do not have the resources, time or budgets available to do the more fancy numerical simulations. So that's today, I'm going to just scrutinize how well some of our simplified liquefaction triggering procedures work. So I'm just going to cover a little bit of background. I'm going to look at how we predict surface manifestation of liquefaction based on cone penetration test methods. We'll do a little bit of comparison between predictions and observations, and we'll look at when it's doing a good job and when it's actually mispredicting, and then scrutinize it a little bit further, and then we can come up with some preliminary conclusions as to where some of this work can go from here. For those that are not completely familiar with liquefaction, when we get earthquake shaking, and we've got areas where there are sandy soils, the water pressures can start to build up and the soils lose strength and things sink into the ground. Near rivers, streams, and estuary boundaries or so, the river banks, stream banks come in, and then when you've got bridges crossing them that don't have enough resistance, they can end up buckling. Things like power poles sink into the ground. Houses perfectly undamaged from the shaking. Not one bit of shaking damage in that house, but just unfortunately completely sinks into the ground. Every time it rains now, that house fills up with water. Things tilt. The interesting thing about this site is that you notice that the house is tilted one way and the garage is tilted the other way. So there is a fair degree of randomness. One might say that it was the grand piano sitting on one side of the house that caused it to tilt one way, and the Harley Davidson sitting on the other side of the garage making it tilt the other way. But liquefaction causes a lot of damage, but it's fairly random. It's not predictable as to which way a house will tilt or not tilt, or a building. Often when liquefaction manifestation comes out, we just know bad things happen. When buildings are a bit heavier, this is a photo from historical earthquake in Japan. Buildings on shallow foundations, they can rotate over and lose their bearing capacity. A little bit awkward getting out of those buildings where the walls all of a sudden become the ceiling. Chambers in the ground can come up. Just the buoyant effects could cause liquefaction to come up. Of the liquefaction causes those chambers to come out of the ground, and it's not just manholes. It's also things like underground fuel tanks come up out of the ground. And just in case we thought it was only a Christchurch problem, here is just some aerial snapshots of some areas in Blenheim following the Kaikoura earthquake. We can see a lot of lateral spreading. Fortunately, in this area, there were no houses. So in Blenheim, they'd built in many of the right areas. We can see the vineyards here, where this area on the river bend has completely dropped. Now, had Blenheim chosen 20 years ago instead to build houses in this area, such as what Christchurch did, that would have been a very sad story for quite a number of households. Fortunately, they chose to develop this area with vineyards, and the impacts were a little bit less dramatic, but nevertheless, the same hazard still exists. This is in Kaikoura, next to one of the creeks where lateral spreading is occurring, and then causing considerable damage. And then this is in Wellington, in the Centreport area. This is actually the damage. About 5 to 10 metres of reclamation on the edge was lost due to the Cook Strait earthquakes in 2013. Really only a baby earthquake, tiny levels of shaking. If there should have been a wake-up call, and then when the Kaikoura earthquake came in 2016, but larger shaking, there was considerable more damage in that port. And this photo in particular shows the wharves, and then in front or behind the wharves, which we can see the land has dropped. That's the reclamation itself. So that makes your container operations and all those vehicles needing to travel about to move those containers almost impossible to use that area. Also significant damage to the wharves and cranes, and so liquefaction is a really big deal. We need to predict it every day. So how do we go about it in industry? Well, we typically make use of cone penetration tests, can make use of other tests as well, but effectively it's a truck that comes along, or a rig, and it pushes a steel rod into the ground. Now that steel rod, as it's pushed into the ground, it's hooked onto a data acquisition system, and it records some fancy measurements, how much resistance there is in pushing this tip into the ground, and also there's a sleeve behind it, and it measures how much friction there is on the sleeve. And from that, a whole lot of fancy calculations get done, but effectively all it is pushing a steel rod into the ground and making a few measurements. And so from that test, we can get a measure of the penetration resistance that we can see coming into the ground. This is one particular CPT test where it's showing a depth versus resistance. This is just a typical log. And then from there, we can start to do a liquefaction evaluation. Now, across New Zealand, 45,000 of these tests have already been collated in the New Zealand Geotechnical Database. Over half of those are in Christchurch, but the other half of those are throughout the rest of the country. So we could either come to a site and look to evaluate, do some testing and evaluate the liquefaction, or we could actually make use of the data that already exists to give it a bit of a sneak preview of what the hazard might be in different areas and do all types of regional modelling. So we then put that through essentially this basic empirical assessment procedure, where on the horizontal axis, we've got the penetration resistance, or a measure of soil density. The harder it is to push that cone into the ground, the more resistant the soil is to liquefaction, or the denser it is, and so the greater resistance we get. The vertical axis is a measure of earthquake strength. And so the higher or the larger the earthquake shaking intensity, the further up the axis we plot. Now, if we end up plotting on above the curve, liquefaction is predicted. If we end up plotting below the curve, we don't predict liquefaction. So when we've got soils where there's a high penetration resistance, so that they're dense, we don't predict liquefaction. When we've got loose soils or very high levels of shaking, we do predict liquefaction. And so we do that for each layer by layer. From those cone penetration tests, we run that through that evaluation procedure, And then we can do that for small earthquakes, medium-sized earthquakes, and large earthquakes. And the profiles that I'm showing on the bottom left-hand side, sorry, bottom right-hand side, literally show the green is the soil layers that are not predicted to liquefy for a low level of shaking, or in the case of the SLS case, and for exactly the same CPT profile for the ULS case, a much larger shaking intensity, we see that there's a lot more liquefaction being predicted, which is the layers in red. We can then integrate those effects, because obviously the case shown for the SLS, where there's only a few layers that are predicted to liquefy, given that there is a thick layer of non-liquefying material over the top, and a small layer of liquefying material predicted to be sandwiched in that soil profile, that's barely going to have a consequence at the ground surface. The case on the right-hand side with the higher shaking intensity, there's a very thick layer of material that's predicted to liquefy, a very thin layer of non-liquefying material sitting over the top, and so we'd expect that to be a lot more consequential. And so we can use indices that integrate that together as a measure of the damage potential. So if we take an area in eastern Christchurch and we take one particular CPT out of the 20,000 CPT in Christchurch, we can then do an analysis of calculate one of those index values, and we can plot that up as a function of shaking intensity. The higher the shaking intensity, the greater the damage potential. We see that liquefaction is somewhat of a binary. At lower shaking intensities, nothing is predicted. Then we come to a certain threshold, and then liquefaction starts to kick in. More and more soil layers liquefy, and the damage potential gets bigger at greater shaking intensities, and then things plateau out. And so that's for one particular CPT. But within that grouping there, which is an area of similar geomorphology and geology and depth to groundwater, we can actually see that there is the CPT within that area says there's actually a bit of variability in what occurs. At low levels of shaking, nothing will occur. At medium levels of shaking, within that area, it's actually a bit of a mixed pot between typically minor to moderate damage, but there'll be some occasional spots where it's more severe and less severe. But we can see the general trend in that area. So this is just showing some of the spatial variability. Now we can look at different areas and group different areas together based on similar geology, geomorphology, and collate those tests together, and we actually see that different areas produce different curves. So we can see the area of coastal dunes where the depth of groundwater is higher, where the penetration resistances are higher, and just the sands are a lot denser, that at high shaking intensities we don't predict any liquefaction. Whereas some of the inland estuarine deposits sitting behind the dunes, we can see that at lower levels of shaking, liquefaction starts to initiate, and then when we get to medium and high levels of liquefaction, we're predicting moderate to severe liquefaction damage. So we get a different set of curves for each area due to soil composition, soil density, depth to groundwater, and just the general spatial variability. Some areas have a lot more variability than others. So some areas uniformly behave well, and some areas uniformly behave badly. So the nice thing we can then do is, here's an Eastern Christchurch example, is where we can collate some of those CPT test results, take them through those models, and then look at what's being predicted. Area D is obviously an area that's quite resistant to liquefaction, and area A is least resistant to liquefaction. If we then take, for example, a magnitude 6 event with a shaking intensity of 0.3 G, we can just directly read from these graphs for the different areas, and we can get the median liquefaction index value, and we can plot that up, which I'm plotting in the middle here, which is showing the mean expected damage within each of those areas, where low LSN values correspond to no to minor predicted liquefaction, and then areas such as C, which are in a sort of a 10 to 15, 15 to 20, is where we'd have more moderate, minor to moderate effects of liquefaction. And then in area A, we'd have more moderate severe predicted liquefaction. So this would be an example of a regional hazard map that's developed. This isn't really a good representation showing the mean hazard, because there's some areas where there's a lot more variability than others. So we can actually do some sampling through these areas and break each of these areas up by tiling it. So breaking each of these geomorphic and geological areas up into 100 metre by 100 metre tiles. And then from area A, we can actually sample that distribution and then provide a realisation showing, within area A, that there'll be some spots where the liquefaction won't be so bad, but overall it's bad. And we'll just show some more of the variability. And so this is a better representation of the liquefaction hazard we would actually expect within that area. It's exactly the same as the mean hazard, but this could give you a sort of a false sense of a uniformity. In fact, that's just a realisation of what it would practically look like. It's not only in Christchurch where we can do this, but also in Wellington. There's a recent study that's been done, very similar process, collating all the geotechnical data together, CPT data within these areas, and then grouping it. And then we can see for a particular shaking scenario, the Wellington fault example, with a magnitude 7.4 event that went off, the shaking intensities that would produce. The liquefaction that's then predicted, the area shown in red is where we'd expect moderate severe damage. The areas in green is minor to moderate, and then the areas in grey are, and blue is where we're not expecting any issues. These little areas in the light green is flatland areas that have not yet been evaluated, but the study is now being widened into those areas as well. All the areas in white, basically a geology, it's hills, it's not flat land, so we wouldn't expect liquefaction within those areas. So how do we know how well these methods are doing? Is it correctly predicting, under-predicting, over-predicting? That's where we can start to make some comparisons between predictions and observations. Just try and get some level of calibration or understanding of how well these methods work. So if we apply those procedures that I just went through, and for the September 2010 earthquake, we can see on the left-hand side the liquefaction that is being predicted across Christchurch, and on the right-hand side is the liquefaction that actually occurred. Not ideal. We can see generally that there is a lot of over-prediction that is occurring, particularly in the western areas of the city, where the liquefaction is significantly being over-predicted. A lot of that is due to particular soil issues within those areas where those liquefaction prediction methods are really struggling to correctly predict the liquefaction. Just a quick overview of this just shows that there is an over-prediction tendency at that particular level of shaking intensity within the Christchurch area. Now if we compare the predictions for the February 2011 Christchurch earthquake, much higher shaking intensity, a bit of a smaller magnitude, and then we compare that with the actual observations of where liquefaction occurred. Once again, we see that there is a over-prediction tendency, but not as severe as, or that over-prediction tendency is not as big as compared to the September 2010 earthquake, where the shaking intensities were lower. It's actually showing us that the prediction of liquefaction is better at higher shaking intensities than it is at the lower shaking intensities. And then if we look at the Valentine's Day earthquake in 2016 in Christchurch, tiny earthquake, but a really nice test. On the left-hand side, we can see what's predicted. On the right-hand side, we see what actually the areas where liquefaction actually occurred. And now we see in eastern and western Christchurch that at least our prediction methods and our observations are in agreement with one another. So when shaking intensities are very low, once again, the methods are correctly predicting. In the east of Christchurch, unfortunately, we're under-predicting the liquefaction relative to where it occurred. So there's a bit of under-prediction occurring at the lower levels of shaking. So now that we've taken a little bit of a global look at things, we've then taken 55 case history sites or 55 sites within Christchurch denoted by the stars, where we've gone and done more detailed evaluations to have a look at what's going on. Many people have been studying different effects with Professor Miško Kubanovsky and Professor Jonathan Bray have been looking at detail scrutinizing these sites, and Professor Brady Cox and Professor Ross Bullinger have been looking at other aspects at these sites. But I'm just going to provide an overview of what these sites show just in terms of general soil profiles. So plotting the just plotting the raw data for each of these sites, what we've done is for each of these sites, we've binned them by the level of shaking that each of these sites experienced. And on the vertical axis, we're showing depth ranging from 0 to 14 meters. On the horizontal axis, we're showing the CPT penetration resistance for the top row of graphs. And on the bottom row of graphs, we're showing the soil behavior index, which is a measure of is the soil sandy or is the soil silty. And then the coloring of the graphs, the blue graphs show the soil profiles where no liquefaction occurred. The red traces, or the red graphs, show the soil profiles where liquefaction manifestation occurred and it was severe, and then the green ones are where it was minor, just bordering. There's a couple of reference lines here. On the top row of graphs, we see the black line here is a reference curve for where, from the simplified methods, for a safety factor of 1, that would be, if you're plotting on the left-hand side of that curve, liquefaction would be predicted if it was a clean sand, and if you're plotting on the right-hand side of the curve, the soils would be too dense, or would be dense enough or would not be liquefying. That just comes directly from that graph as a reworking. And once again, on the bottom row of graphs, we plot a reference line of I sub C of 1.8, which is a measure if the soils have a value of 1.8 or less, they are a nice clean sand. And also the other dotted line, which is an I sub C of 2.6, that's where the soils are quite silty and clay-like in behaviour, and values greater than, or soil layers with a value greater than 2.6 are considered too plastic or in behaviour to liquefy. What we can see when we just look at this raw data is that at low levels of shaking, we're predicting very little liquefaction, as we would expect at levels of shaking of less than 0.2 G. From 0.2 G to 0.3 G, we can see that some soil profiles liquefaction actually occurs. And the typical characteristics of these soil profiles, really the difference between the soil profiles that are liquefying and aren't liquefying, which is the difference between the blue and the red, really shows up in this bottom set of graphs here, where the soil profiles that are liquefying and causing a manifestation at the ground surface, a lot of damage, are soil profiles where there's thick, clean deposits of sand with I sub C values of around 1.8 or less. The soil profiles that are not liquefying are soil profiles where these blue lines keep on crossing in and out from that are interlayered sands and silt. So soil profiles where the soil was just heavily stratified, where it's a sand and a silt and a sand and a silt, quite layered systems. So layered systems are not causing a manifestation problem or having damage at the ground surface, whereas non-layered systems or thick deposits of clean sand are resulting in significant damage. Now, all of these CPT profiles that we are examining here, most of them are ones where liquefaction was being predicted. So it starts to provide a little bit of insight of where our methods might be going wrong or mispredicting. What is interesting is that as we increase the shaking intensity, so areas where the shaking intensities were a lot higher, greater than 0.4 G, we start to see that far less blue lines appearing on the page and red lines are appearing. So even these interlayered sites of sands and silts are starting to liquefy. So it's when the shaking intensity gets high enough, things do start to liquefy. There's a lot more going on that graph than what I just looked at, so we need to dissect it a little bit more. And so that's where we can develop a bit of a framework for comparing the prediction against observation. Where we have a correct prediction, or where of liquefaction occurring, and it indeed occurs, we can say that that's a true positive. So true positive is where we're predicting liquefaction, and indeed it occurs. A true negative is where we're predicting that liquefaction shouldn't occur, and indeed when we compare it with earthquakes and where nothing occurred, then that would be a true negative. Incorrect predictions, where we predict liquefaction to occur, and indeed, and it doesn't, is a false positive. And where liquefaction doesn't occur, but we are predicting, where it doesn't occur, but we are predicting it to occur, is a false negative. So if we develop this framework of true positives being good, and true negatives, that's a correct prediction, false positives and false negatives is an incorrect prediction, and we then start dividing up these curves a little bit more, we get a little bit more insight. So now when we take the same curves that I showed before, but now a subset of the ones where we were not predicting, also where we were predicting liquefaction, and and it indeed is occurring, and then we start examining what does the raw data for that data set look like. We can see that generally the CPT tip resistances are below the reference line. They're nice, thick, clean deposits of sand. So this is cases where the liquefaction is being predicted, the method is doing a good job, and indeed it's occurring. True negative cases, the cases where liquefaction is not predicted and it's not occurring, generally where the CPT tip resistances are a lot higher relative to the reference curve, so the sands are denser. And so once again, when it's nice, thick, clean deposits of sand, but where the soils are very dense, liquefaction isn't occurring. So when we have these type of soil profiles, we know that we can have confidence in our liquefaction triggering or our liquefaction predictions. When we examine the false negatives, they become a little bit more interesting, and they're perhaps, from an industry perspective, the more troublesome ones or the worrying ones. Because these are areas where we are not predicting liquefaction, but it is occurring. And so in these situations, we might actually be under-designing our bridge or our building foundations. The typical characteristics of false negatives are where there are thick, clean deposits of sand with I sub C values of 1.8, and the CPT profiles, it might be a little bit that dips below 1, but a lot just sits above 1, but it's not the consistent profile. So there are some layers that are liquefying, but the effect of the non-liquefying layers also seems to exacerbate or contribute to the damage. And detailed numerical studies by Professor Mieszko Kubanowski and some of the system response work that he has been working on through numerical modeling has shown some of the more detailed mechanisms of what's happening for these cases. And then the false positive cases, the ones that seem to be causing a significant over-prediction in Christchurch, particularly in Western Christchurch, are cases where liquefaction, severe liquefaction is being predicted, and nothing is being observed. Not one bit of liquefaction is being observed. So these areas are performing really well, yet our methods are suggesting that we'll be getting a lot of damage. Typical characteristics that we can now see of those is highly interlayered soil profiles. There might be layers of sand in there, but they're trapped in between layers of silt. And so while there's a lot of micro layers that are predicted to liquefy, they're not thick, clean deposits of sand. They're just little layers of sand trapped between the silt and clay layers, and they are not, it's not resulting in damage at the ground surface. So when we see soil profiles like this, and we're doing a liquefaction prediction, this now can give us a bit of a clue that we're potentially going to be over-predicting liquefaction. How we in the future might build some of these insights of characteristics of soil profiles that might be tending towards over-prediction or under-prediction into the liquefaction evaluation procedures is some work that is now underway. But it's first been scrutinizing what are the conditions that lead to over or under predictions. So if we just then start plotting up at the different levels of shaking, the percentage of sites where we're getting true positive and true negative and false positive and false negative predictions, we see at higher levels of shaking, more of the soil, more of the sites are liquefying, and we see that as the shaking intensity increases, the amount of true positive predictions of liquefaction is increasing. At lower levels of shaking, we're getting a lot more true negative, so not predicting liquefaction, and indeed it's not occurring. And so we see that our true negative sites slowly become true positive sites as the shaking intensity increases, as we would expect. But it's the false negative and false positive sites. The false positives do seem to decrease a little bit with shaking intensity, but we can see that well over half of our liquefaction of sites where we predict liquefaction, there's actually an over-prediction or an under-prediction tendency. So there's a lot of work to do in this space, research work, to actually try and improve these procedures. But the starting point is actually to evaluate how good are these procedures and to develop a baseline. Now, if we extend this back to lower levels of shaking, if we put, at very low shaking intensities, indeed all these methods become a true negative. So if we now bring these together for a certain level of band of shaking, where we bring the true positives, true negative, false negatives and false positives together at one particular shaking intensity, a band from 0.2 G to 0.3 G, we can see how these soil profiles compare side by side. The red ones are where liquefaction has occurred, the blue ones is where liquefaction didn't occur, and then the positive ones is where there's a correct prediction. The true is where there's a correct prediction, the two on the left, and the two on the right, where there's a false prediction. We can very quickly see now in contrast how these different soil profiles compare. And so, what we've learned from this study and research is that effectively anywhere where we see thick deposits of clean sand, where the soils have a lower density, even perhaps a density that sits above the reference line but some layers below, that those are sites where liquefaction is occurring, and perhaps where things are near the threshold but there's a little bit of under-prediction occurring. And then when there is a lot of interlayering, that's when we're getting a lot of false positive or over-prediction. Being able to identify these factors then help in a forward analysis sense, because if we can identify geological deposits that have those characteristics, we can then downgrade or reduce the predicted liquefaction potential in those areas. Just to avoid the study becoming Christchurch centric and to test this out in other areas of New Zealand, we've a large team of also of students and master students have also collated all the case histories together from New Zealand where liquefaction has been observed from other historical earthquakes. Here we're showing the results from where the liquefaction was mapped in the 1987 Edgecumbe earthquake. The areas are shown outlined in yellow, where it's very definite that liquefaction was observed and there's photographic evidence. The areas outlined in black is where it may have occurred, but we're not completely certain, or there's just a little bit more uncertainty there that's based on written descriptions, but not photographic evidence. And then all the areas outside of those areas are where there was no liquefaction observed with confidence. The dots sitting on top is the predicted liquefaction for CPTs within the Whakatane area. The predicted liquefaction for the 1987 Edgecumbe earthquake. It's good to see that in the eastern side of Whakatane, the western side, that liquefaction is correctly being predicted. But we also see of the CBD on the eastern side of Whakatane that there's a lot of liquefaction being predicted, and nothing occurred. That whole township, the CBD, there was no ground deformations, no damage to those buildings from liquefaction. There was just some shake damage to those buildings. So once again, we have a problem. We can do the same for the Blenheim area, where the liquefaction has been mapped, and compare the liquefaction predictions, which we haven't got on these maps here, but we're just showing the areas where liquefaction was actually mapped. We've done a similar exercise in Hastings and Napier for the 1931 earthquake, and doing similar exercises on the west coast, where liquefaction occurred and didn't occur for the 1968 Inangahua earthquake and 1929 Murchison earthquakes. And then we can just bring some of these different areas of New Zealand together, where we can show the soil profiles from the 1987 Edgecumbe or in the Whakatane area, and how they performed in the Edgecumbe earthquake, some of the Christchurch ones, and some of the Kaikoura soil profiles or Blenheim soil profiles, and how they performed in the Kaikoura earthquake. The set of graphs on the left are the true positives, so where liquefaction occurred and it was predicted, and the graphs on the left are cases where liquefaction didn't occur but it was predicted. So we've got the true positive and the false positive prediction. So for all of these soil profiles, we're predicting liquefaction. The ones on the left is where it's doing a good job. The ones on the right is where there's over-prediction occurring. If we then look at the different areas and what we're seeing, once again, the over-predictions areas in Whakatane, there seems to be a lot of interlayering of soils, similar to Christchurch, albeit that within the Whakatane area at greater depths, there is thicker deposits of clean sand, but being capped by considerable thickness, up to 4 meters of sand, which is interlayered, sands and silts. And in Kaikoura, in the Blenheim area, where over-prediction is occurring, once again, a lot of interlayering. So it's not just within the Christchurch area, south and the western side of Christchurch, where we have these soil profile systems where there's over-prediction occurring. It's occurring in other areas of New Zealand as well. So that can give us some confidence going forward that we can actually make adjustments or modifications to the liquefaction evaluation procedures, that where we have certain soil profiles, where there's interlayering, that perhaps the predicted liquefaction can be downgraded, and where there's areas where there's thick deposits of clean sand, that perhaps the predicted liquefaction in such areas needs to be upgraded a little bit. Those changes to the framework are still a sort of a work in progress, and what needs to be made. This work so far is focused on what are the typical characteristics, what's leading to an over-prediction, what's leading to an under-prediction using these simplified methods. And so that's really the conclusions that are wrapped up in here, that true positive sites are sites where we're predicting liquefaction, and where there's shallow layers of thick or lower, and lower density clean sands. We're predicting liquefaction, it's occurring, and we can have confidence there. The false negative sites, so there's thick layers of clean sand, but with variable relative density. Some soil layers are liquefying, some are not, but soil layers that are affecting soil layers that are not, and they're actually resulting in more liquefaction than we're actually predicting. For the true negative sites, that's where we just either, there's two reasons for true negatives. It's either because the soil is quite silty and plastic, the entire profile, or the very dense soil profiles. And then for the false positive, it's highly interlayered systems, particularly within the top 5 meters. So further work that we're now doing is this work is sort of looking to map all the case histories of liquefaction in New Zealand. A database has been pulled together from the historical earthquakes wherever liquefaction has been observed. Equally, an effort needs to go in on where liquefaction hasn't been observed for a particular earthquake, because too often we only document where liquefaction occurred, where there were stop bank failures, where there were building failures. And it is a lot harder to go back into the records and actually positively identify areas that weren't affected by liquefaction. However, there's considerable effort going into that, because those areas need to be documented and evaluated, because they are equally helpful to evaluate where there's false positive predictions going on. As we expand to different areas of where liquefaction did and didn't occur for different earthquakes in New Zealand, and then using some of the ground motion models from those specific earthquakes that the flagship 1 group within QuakeCoRE are developing, we can then do the predictions, do further examination of comparisons to continue to identify the characteristics of true positive, true negative, false positive, and false negative sites, and then we can use those insights to make improvements to the simplified procedures. And so with that, that ends my talk, and very happy to take questions now.
Great, thanks, Sjoerd. This is Chris at UC. Liam said he had to shoot off, so I'm taking over as the question fielder. If anyone has any questions, either in the direct audience or on Zoom, welcome to take those now.
Morning, Uma here from JNS Science. Very nice talk, Sjoerd. Thanks for that. Just a quick question, as I'm very new to this, the test, the CPT test, did you do after every earthquake, or did you do once? I mean, just a question about the timing of the test and the observation and prediction you are comparing.
Okay. So almost all of the CPTs that are available in the New Zealand Geotechnical Database, and when that have been done when we're evaluating or scrutinising these procedures, have been undertaken after the earthquakes, and in the case of the Edgecumbe earthquake, 20 odd years later. In the case of the Christchurch earthquakes, after the earthquakes. Now, there are in Christchurch about 30 or 40 CPTs that were pushed before the earthquakes. Very little geotechnical investigation was actually undertaken in Christchurch prior to the earthquakes. Liquefaction was largely a hazard that ECAN recorded as a potential hazard, but no one ever did anything about it, or barely evaluated and let it inform design. So there's very few pre-earthquake CPTs. When we compare those pre-earthquake CPTs with post-earthquake CPTs, we see that there is very little difference in the CPT tip resistance and the sleeve frictions. So while there appears to be, the ground might have increased in density just slightly, but it hardly registers as a change. And we have seen from the repeated earthquakes that liquefaction just keeps on occurring It doesn't matter if we've had one earthquake or another earthquake. We had the large February earthquake, then the June earthquake and December earthquake occurred, and liquefaction occurred again. So the CPT or the ground profile, the characteristics, the relative density of the ground is not significantly changing as a result of an earthquake, and therefore, while the CPTs are all a post-earthquake CPT data set, they are not too dissimilar to what the ground conditions would have been pre-earthquake.
Thank you so much.
Hello, this is Jagdish from University of Canterbury. It was interesting to see that for the February earthquake, there was an over-prediction where the shaking level was high. And if you compare that to the Valentine events, where the shaking level was low, there is an under-prediction. So there is a kind of contrary results to each other. Now, I was just wondering, what's the physical reason? Is it because of the uncertainty in the shear wave velocity profile? Is it because of the limitation of the method? Or is it because of both?
These are empirical methods. I have shown it in the slide extremely simplified. But this graph shown here is effectively a line that has been developed. It's an empirical based line based on case histories of soil layers that have been identified to have liquefied from earthquakes around the world. And on this side, soil layers where no liquefaction has occurred. And it's effectively, they've divided the liquefaction cases and the no liquefaction cases from a case history data set, and then put a dividing line in between there. Within that, there appear points of no liquefaction case histories occur on the left of the graph, and a few occur on the right-hand side of the graph. So it is an empirical based equation that has been set. It just is that when you're sort of sitting near that boundary, there can be a little bit of under and over prediction. The further you are away from these boundaries, the better your prediction should be. So when your earthquake shaking gets very, very large, you tend to move further away from this boundary, and your predictions should indeed become more accurate. When your shaking intensities get very low, you move once again closer away from these boundaries, and your liquefaction predictions should become more accurate. As you approach these boundaries, your liquefaction predictions should become a little bit more, we'd expect them to become more variable. But then when we're at the other problem that we identified is when we're sitting in this zone here, when soil profiles are actually interlayered, we are treating each soil layer as, analyzing it discretely. We're analysing each soil layer one by one, packaging them all together, but really what we're doing is we're summing up the contribution of each soil layer, where in an actual, as a sum of discrete parts, when in actual fact it is an entire system that is responding. And some of the work by Mieszko Krobanowski, is showing that we've really, in the future, got to move away from a discrete layer analysis that we then sort of combine together to start thinking about overall system response. And the work that we've been showing here is that when you, for example, have a soil profile or a soil system that is an interlayered system, it's responding differently than when we have a soil system which is a thick, clean deposits of sand.
Yep, makes sense. Thanks.
Yeah, Claudio from the University of Canterbury. Sjoerd, may you show again the slides where you it's one of the very last ones where you compare the case histories of false positive, false negatives from. Yeah.
This one?
Yes. It seems to me that actually for the Kaikoura event, the profiles basically look the same, whether they're false positive or too positive. Then there are the highly interbedded systems, are the false positive for Canterbury, but then these profiles look way more similar to the true positives of the Edgecumbe earthquake rather than the false positives. So let's say the two cases, Edgecumbe and Canterbury, look for swapped. So my question is at this point, in which kind of soils, which mineralogy, where do we find in the three cases?
Well, in Christchurch, it is the quartz-based sands. In Edgecumbe, in Whakatane, we have quartz-based sands, but a lot of pumice based soils thrown into the mix. The CPT profiles from the Kaikoura earthquake that I'm showing here come from Blenheim. I don't know what the soil mineralogies are there and what that is. So far I'm showing a framework and how we can divide these things up. There needs to still be a lot more detailed examination and of other areas as well, the west coast of New Zealand and Napier. Preliminary work we've done in Napier is showing a lot of false positives there as well, but also some false negatives. And so mineralogy is one of these aspects that needs to be examined through this framework. I can't answer your question as what the mineralogies are in every place, but it's one of the variables that we need to sort of look at as well.
Just for me, that from this slide, the influence of the highly layering across the soil profile, sounds like a reasonable explanation for the Canterbury site, but it doesn't seem to me to be so obvious for the other systems. So there could be other factors which play a role. But
it is a work in progress. It's not a finalized piece of work. Really, even the preliminary work has shown a lot of insights already.
Hi there, Ribu here from University of Canterbury. I guess this kind of builds on from Claudia's question. The simplified procedures have been based mainly on clean sands with few finds. Those are where the lines are based on, when you were showing those earlier. Yeah, so those are based on mainly clean sands with some small fraction of finds. Now, I guess my question is, in Christchurch, we saw that there were layered soils or mixtured soils. In Wellington as well, we do see, even in Blenheim as well, gravels also start coming into play. So I guess my question here is, when you start looking at the applicability and the performance of simplified procedures, what role do you think, the soil, I guess, grain composition plays in it? Surely that also has a large influence over, more than just system response as well.
Yes. Yeah, so I have shown a very simplified version of this presentation. It is more detailed. The simplified procedures do make corrections for your fines composition. The more fines there are in the soil, the more correction that is made. The simplified procedures have been developed. The predominant case history, or most of the case histories developing that have led into the development of these simplified procedures do indeed come from clean sands. There's been a lot of work also done on silty sands and silts, and there are correction procedures for when there is fines in the in the sand, and how you make adjustment, and you make adjustments for those. Now, the nice thing is that this framework here has been able to basically evaluate when we get, are those corrections, are they indeed doing a good job, or when we have silty soils, are they not, is there a lot of false positive and false negative prediction going on? So we can once again scrutinize not only the performance in sandy soils, but also in silty soils. The work shown to date is that silts themselves, we're more coming across an issue of interlayered sand and silt layers where liquefaction is being predicted within the sand layers, where that's leading to false positive prediction of liquefaction, compared to sites that are just pure silts. Pure silts, we don't have a lot of case histories of pure silts, and whether or not they're liquefying, but it's one of the things that we're hoping in the case histories to just find and scrutinize. Whether or not the simplified procedures are appropriate, there is no commentary on that. The industry standard is to apply the simplified procedures everywhere. There is no, different method for fine grain material or silts or for sands or gravels. And so this is what we're attempting to do, is to say, well, the industry-based methods, how well do they do, and where does adjustments or changes need to be made in which conditions? And that is mineralogy, that could be certain characteristics of soil profiles, that might also be for silts versus sands. So that the study is attempting to evaluate all the different factors.
Thank you.
Okay, is there any more questions? Doesn't seem like it. So thanks, Sjoerd. That was very interesting and informative. We really appreciate you taking the time out.
Thank you.